This is PASC25, highlights from this mini symposium. I am here with Laurent Villard, who was the organizer of machine learning methods for the simulation of magnetic fusion plasmas. Then I am with Stefan Brunner, who organized the mini symposium, Advanced Simulations of the Plasma Edge Region in Magnetic Fusion Devices. You all have very long titles. And I am with Eric Sonnendrucker, who organized the mini symposium, Mathematical Developments for Magnetic Fusion HPC Applications. Then I'm going to ask you to please tell us what were the mini symposia about. Of course, they're all about the fusion and plasma, but if you can also briefly comment on how do they fit with the theme of the conference, supercomputing for sustainable development. Please.
So it's indeed all about magnetic fusion, and magnetic fusion has an obvious goal of finding a new energy source, which is virtually inexhaustible, which is environmentally benign. So that's one of the few options we have, if you think about it, on the long term for our energy production worldwide. So that's for the, say, society impact of this research, the general frame into which our research is placed. Now, more specifically, we have in our three respective presentations accent more either on the high-performance computing and applications or the numerical methods. So respectively, Stefan and Eric can talk more about it. And one aspect which is more recent is what is the role of machine learning and AI in general in helping us along the way. And that was the first time actually that in the context of a PASC session that we organized a specific mini symposium with this theme, say, on AI and machine learning.
Nowadays is the general theme of all also more traditional sciences to understand how machine learning and AI can help the research. So what are the highlights or the take-home messages from your respective discussions?
Yeah, for example, my mini symposium was more focused on new algorithms and mathematical methods to make the code faster and more efficient on HPC systems. For example, we are solving the Vlasov equation, which is a high-dimensional PDE in 6-dimensional. And when there's a big bottleneck, when you have multiple nodes, multiple GPUs in communications, and there we had a talk which was focused on this, trying to find a method to communicate data which is asynchronous, which is well known in HPC, but this needed to be adapted specifically for this 6-dimensional system. And so we got new insights and new ideas on how to do this, which will be useful for many types of Vlasov codes which use different techniques. And then also there are often bottlenecks with, when you solve for example, for the neutrals in a plasma simulation, you have some non-local equations to solve which yield dense matrices, and there are new tricks based on hierarchical matrices where you can make this sparser and more efficient. So these are mathematical tools. And then we have also had a talk on geometric numerical methods where you have specific techniques to do discretization which keep the Hamiltonian structure of the initial models such that you are long time stable, and this gives you a more robust code which is guaranteed stable for very long time simulation and can conserve energy very accurately.
Stefan, and what were the highlights from your mini symposium besides what has been already said?
Well, the mini symposium I was chairing was focusing on the edge region of magnetic fusion plasmas, that is tokamak accelerators, and this is a very challenging area because there are very steep pressure gradients, very large amplitude fluctuations, interaction with the wall, there are neutrals, many types of impurities, complex plasma wall boundary conditions, and I think the mini symposium illustrated that to address this very complex problem, we need high performance computers, but there's a true need also for improvements in mathematical methods, so applied math, naturally porting the codes to really harness the new generation computers and improving the physical models with always more realistic physical conditions. Yeah.
Makes sense. So one step further for each one of you. So what comes next? One point for each of you.
Oh, I don't have.
For you to not lose the momentum of gained by at the PASC conference.
So I will consult my crystal ball here and see what are the next steps. No, the next step are in terms of machine learning and AI. I'm not a specialist myself, but from what I see, there are two axis where this can develop. It's either to help us, because there's always a compromise. Either you do the very detailed, direct numerical simulation, for example, of turbulence, which is one of the great challenges of this millennium.
Yes.
We heard about
today
it
also in
for
the
neutral fluid, and I can
dialogue,
tell you that adding the electromagnetic interaction does not simplify our life. So anyway, help us to maybe identify, because we have very few ammunition, if you wish, because there's only very few runs with complete physics that we can make. So maybe machine learning will help us to identify where and when to do the most meaningful, complete direct numerical simulation. That's one point. The other axis is to go towards surrogate models or simplified models, to go towards, and it's already happening now, but it will further develop, to go to real-time control of plasma. So you want to use really extremely fast models. Now we are really talking about models that can act within a few milliseconds to control the plasma, because it's multiple physics. Now it's a question of integrating multiple signals, magnetic signals, and in relation to different physics and different time scales, in a quick enough way so that you can even dynamically control the plasma. That's the other. From
your mini symposium, what would be the next step natural next step to follow?
So what we often see, not only here in this mini symposium, is that the development of mathematical methods and the real applications are often a little bit decoupled. You have the mathematical methods which are developed in a toy code, and the time for implementation or find somebody who will implement it in the real production code is not always simple. And because the people developing the algorithm, once it's published, have no interest directly in writing this in a production code. I think this is one of the issues we can see here. And so now people are also developing software environments that can be useful to test things, but then a real production code is still something else, and the gap between the new method and the production code will be hard to fill.
Stefan, for you?
I think the future, one has to, concerning these edge simulation codes, one has to further step on all these fronts of applied math, improving the physical models and computer science. And so I think it's really a progress that has been happening in parallel and has to continue in that way. And ideas came up using machine learning and optimizing these codes, maybe in providing the core turbulence provides the boundary conditions to the edge simulations, and maybe there, for instance, surrogate models can be used. So there are all sorts of ideas that in the frame of this meeting came up, and which should be pursued.
Which is the purpose of having an interdisciplinary PASC conference. We still are all looking forward the first nuclear fusion plant, but waiting for that in 2050, right? That's the target I heard. But thank you very much for joining us, and thank you all.
Thank you. Thank you.